Example number 1. It already tells it to us, but recognizing it's a Y system helps us to remember that when we come back over to our equation sheet, that we have the I on the phase, right? I phase equals I line, and that is actually true twice because it's true on both the phase of the source and the phase on the load side. All of those are the same. The V, that's not the case, right? The V line equals V phase root 3 angle 30. And once I have that, recognizing it's my YY system, so these are how I'm going to relate these, it's just a matter of making it first the single phase equivalent. So I can convert this into an EAN. Consider, all right, I'm just taking this portion right here and I'm redrawing it because what I'm doing is I'm considering that these two neutrals can connect because they're like ground. There's no line impedances. And then on this other side, I have 10 minus J 15. And that's it. Here's lowercase on that matching this up here. And there's my single phase equivalent. I'm already given EAN. So now let's calculate I that's going throughout this circuit. It's all the same current because it is a tiny little series circuit. We already said that I phase line and I phase on the load side all equal each other. So using our favorite law, V equals IZ, I equals V over Z, AN, AN, AN. The voltage there, 277 angle negative 30. The Z, 10 minus J15. The I comes out to 15.365 amps, angle 26.3 degrees. So now complex power, because I'm going to take it of a single phase, and then we're going to multiply that by 3. So of my single phase, I have the I complex conjugate. And of the single phase, that is the AN and the AN. We have both of those already. This is 277 angle negative 30. And then the I, 15.365 angle complex conjugate. So it's a negative 26.3 degrees. And the S, complex power of a single phase, is equal to 4.256 kilovolt amps, angle negative 56.3 degrees. That is in the polar form. So what that's telling us is the apparent power. Right here is the S total, the S of a single phase. Then I can go from polar across to rectangular. Don't even have to solve for anything. If you want to, you can with the cosine theta, the theta being at 56.3 there. But I pull this out, minus 3.54 J kilovar. And this is my P of a single phase. This is my Q of a single phase. Note that it is capacitive since there's a negative J component there. Now, the easiest step in the world, multiply this by 3. And when I multiply that by 3, I get 12.77 kVA. That is my S total. Just multiply 4.256 times 3. Multiply that P of a single phase times 3. All right, times 3, times 3, times 3 takes it from a single phase to 3-phase power. P total, 7.08 kilowatts. Q total equals 10.62 kVAR capacitive. You could also call it negative 10.62 kVAR, and the negative would tell me it's capacitive. Last one is we need the power factor, FP. You can do P over S. You can do it of a single phase. You can also do P total over S total. When you're multiplying both by 3, the 3's would cancel out and it's the same ratio. Or we could take the cosine of 56.3 degrees. Either way, it comes out to 0.555. And that would be a leading power factor because it is capacitive. And there we have that whole problem.